Okay.
Yeah.
Hello everyone, we are Project Clayton, one of the international teams of the course, and we're working with Dayton, Ohio University. Our counterpart, Rodrigo Valle, is a professor of a technical school from Kilakawi, and with 5 students he challenged us with the following. Water loss in crops under greenhouses due to evapotranspiration. Let's start by giving 2 main definitions. Evapotranspiration is the sum of water evaporation from the soil and the transpiration of plants, and the greenhouse is basically a closed structure which allows for the delimitation of crop compartment in which the inner climate differs from the outdoors. After we mapped our context based on bibliographic sources and remote field research, we traveled to Vilagawin and made the following field research activities. We made 27 interviews to students, school teachers, and professional people from the agricultural area, and 15 decision matrices with which we aimed to analyze their motivations regarding different agricultural activities. And we did photographic comparisons between 9 different greenhouses. With all this information, we realized that there's not a structured irrigation culture in Kilakawi, for which they don't have really control over irrigation systems. This means that they are using more water than they really need for irrigating, and they're liberating more humidity to the atmosphere that finally ends up by condensating in the shape of water drops over the surface of the greenhouse. And in addition, with the diminishing rains over the last years in the region, we converged into the following opportunity: to take advantage of relative humidity excess inside the greenhouse for reuse in irrigation. So we started analyzing our data focused on this opportunity. The first thing we did was to codify all of our interviews, getting 10 codes and 30 zip codes to have a better cultural background understanding. We quantified all of these codes, we find different relationships between them, and we draw different patterns to get to these profiles in which we stacked all this and we clustered all of our interviews to get to our personas. Pablo Moreno, who is the countryside lover, comes from a small farmer's family, and he's going to be the one with most interaction with the greenhouse compared with the other personas. He is really careful about plants and the environment. On another hand, we have Camilo Marin, who is the forest. He doesn't really feel that he belongs to the school, and he doesn't think he's going to have an agricultural future. He doesn't want to work in it. And he's indifferent with the greenhouse and its maintenance. And finally, we have Ignacio Cayumanque, who comes from a Mapuche family, and he really feels strongly attached with vegetation and animals. And his main worry is to keep the plant's process and development in a natural way.
Knowing all this, we're able to present our 3 solution concepts based on our photo analysis and the different references that we found. In addition to this, we have our requirement list that mainly said that the solution must be autonomous, it must be affordable for the small farmers, and it must be adaptable to the different greenhouses. So, our first concept is the humidity membrane. It's based on a thermodynamic phenomenon in which heat moves from colder spaces, from hot spaces to colder spaces to have a thermal equilibrium. So we're aiming to intervene in their actual ventilation systems, such as the door or the window, with an semi-permeable membrane that will let air out, but will trap water molecules that will fall over an hydrophobic surface and to let water flow to a water container. This is because our counterpart wanted to work this way, but we haven't discarded yet the possibility to find a better storage for water that can be adaptable to the different greenhouses. So the students can see the whole process of water, and after that they can harvest it and move it to the main container. Because we find in our analysis that something that motivates students is that the activity must be interactive, so this will work. The main thrust of this idea is that it's not invasive to the greenhouse, It doesn't change the routine of the small farmer, and it has an easy installation and maintenance. But the main problem is that have a localized space, so the amount of water that we can accumulate is not too much. Our second concept is the natural condenser. It is based on in the mix of a conductive material and the Bernoulli effect, which says that if we decrease the flow area of an ideal gas, the temperature will also decrease. Also, we analyzed our photos of the greenhouse, and we found that there is a space non-used at the side of the greenhouse near the walls that we can occupy. So we want to take advantage of this space by creating a cooling system that will cool a conductive material that will liberate heat to the ground and to the cool closed space at the side. So water can condense over the surface and flow again to the main container that was explained in the concept before. The main thrust of this idea is that it is easy to replicate because it uses affordable materials, and also it optimizes a dead space inside the greenhouse by providing the minimum shadow possible. The main problem is it has a complex installation because it involves underground pipes, and it has less water accumulation than an idea that can be installed in a higher place.
Our third concept is the electric condenser that comes from hydrophobic and hydrophilic materials, water polarity and fluid sensitive. As you can see, there's a lot of unused space in the ceiling of the greenhouse where moisture tends to accumulate. We propose to install an electrically charged, transparent structure that will turn on depending on the humidity rate and according to the ideal of the plants. This charged structure will attract the positive side of the water molecules, attracting them to an hydrophobic surface, making them flow down to a hydrophobic pipe and directing them to the water container following the same system that we described before. Here's a front cut of what it would look like. The pros of this concept is that it doesn't intervene with the walking way or the plants, and that it assures more water accumulation. The cons are that it needs electrical power and it might be not so easy to replicate. By comparing our three concepts, we decided to follow with the electric condenser, which we call NAMIP. Now, how will our personas interact with the system? The countryside lover is going to like the system because it will allow him to to save important resources, which is water, and will allow and he will have a high interaction inside the greenhouse by harvesting water. The passive is going to be very comfortable with the solution because by being in height, it's going to be non-invasive. It will also permit a better development of plants and by diminishing the air humidity. Finally, the forest, he really likes technology, so he's going to take care of the device, and he will also like it because he will be able to see the whole process. Finally, it's important to mention that we based all of our concepts on physical principles, and that even though we already chose one, we still have to discuss it with the other members of our team from the University of Dayton to follow the process.